All right, hello everybody. We are group four in the measurements course. My name is Neodon,
My name is Brian Rogers.
And I'm D'Angelo Gibito.
and we did our tachometer based on the fly ball instead of the eddy currents.
All right. Centrifugal governors, the foundational principle behind our design, are devices used to regulate machinery speed. They do this by adjusting input flow based on rotational speed, ensuring consistency and stability in the system. Historically, centrifugal governors are essential components in steam engines, where they control the flow of steam to maintain a constant speed regardless of changes in load. For example, if the engine started to run faster, the governor would automatically reduce the steam flow, bringing the speed back down to its set point. This same concept has evolved into modern applications, such as snowmobiles and ATVs. In these machines, centrifugal governors are used to automatically adjust the transmission pulley ratio based on the engine's rotational speed. This ensures that the power is delivered efficiently across a wide range of operating conditions. The theory behind centrifugal governors, and by extension the flyball tachometer, relies on the interplay of forces. When the system spins, the horizontal centripetal force acting on each ball is the result of two key forces: gravity and the tension in the connecting rods. These forces work together to keep the balls in motion around the central axis. However, as the rotational velocity increases, another force comes into play: the reactive centrifugal force. This force causes the balls to move outward from the center, and the degree of this outward motion is directly correlated with the speed of rotation. By measuring the displacement of the balls, the rotational speed can be accurately calculated. In summary, the flyball tachometer embodies a principle that has been central to mechanical engineering. It provides a direct and intuitive way to measure angular velocity using only mechanical and physical principles. Next slide. Now that we have established the theoretical foundation, let's transition to the design of our flyball tachometer. This project required careful planning and precise execution to ensure that the device operates efficiently and accurately. Let's start with the main components of our design. First, the counterweights. Each counterweight is 100 grams. These provide the necessary mass for generating the centrifugal effect as the tachometer spins. Next, the bevel gear. To control the system of the speed of the system, we implemented a 1:4 gear reduction ratio. This means that for every 4 rotations of the motor, the flyball assembly completes just 1 rotation. This reduction limits the maximum speed of the tachometer to a manageable range of 0 to 3000 RPM. Next, the spring mechanism. The spring plays a crucial role in balancing the centrifugal forces. It provides the necessary tension to counteract the outward movement of the balls, creating a direct relationship between the displacement of the spring and the rotational speed. Next, the ultrasonic sensor. To measure this displacement with precision, we integrated an ultrasonic sensor. This sensor detects the linear movement of a measuring stick attached to the flyball assembly, translating the physical motion into RPM data. Next, the tachometer frame. The frame of the device was 3D printed using PETG filament with 100% infill. This material was chosen for its strength and durability, ensuring the structure can withstand the forces involved in operation. Lastly, the bearings. We incorporated radial and linear ball bearings to minimize friction within the system. This reduces wear and tear on the components and ensures smooth, consistent operation over time. At the heart of our system is a powerful motor, a 0 to 48 volt DC spindle motor, capable of delivering 0.5 newton meters of torque and achieving speeds of up to 12,000 RPM. While the motor operates at high speeds, the gear reduction system brings this down to a level suitable for our measurements, ensuring accuracy without compromising the integrity of the system. One of the most innovative aspects of our design is the use of the ultrasonic sensor to measure displacement. By converting the physical movement of the measuring stick into a digital signal, we can directly correlate the sensor's output to the rotational speed of the system. This integration of modern sensor technology with classical mechanical principles enhances the accuracy and reliability of our tachometer. Of course, the design process was not without its challenges. One significant issue we faced was minimizing friction within the system. To address this, we selected high-quality ball bearings, which reduced resistance and ensures smooth operation. Another challenge was ensuring the accuracy of the ultrasonic sensor's readings. Small fluctuations in the sensor output could lead to errors in the calculated RPM. To mitigate this, we carefully calibrated the sensor and adjusted its positioning to maximize accuracy. Additionally, we implemented a method to average multiple readings from the sensor, smoothing out any inconsistencies. Finally, the tachometer frame presented its own set of challenges. Being 3D printed, the tolerances of the components were initially not tight enough, resulting in some wobbling of the rotating shaft. We corrected this by adjusting the tolerances in the design files and reprinting the components for a more precise fit. This adjustment significantly improved the stability of the system. Next slide.
Okay, so here I'm gonna play a video of our tachometer working.
Like 1.1 volts.
And on the left here, you can see our physical design of our tachometer with a 3D printed white stand to as a ruler to measure the RPM.
Like 1.1 volts.
And here's our actuation. As you can see on the left is our rest position. This is without the motor at 0 RPM and at rest. And on the right is the max linear displacement of the system. And the implementation and data collection on this slide, we're looking at key aspects of our data collection implementation process. First, our nominal sensor reading or our linear displacement offset starts at 62 millimeters according to the ultrasonic sensor and spans a range between 0 to 2 volts. This will provide us a baseline for our measurements. Next, we use an ultrasonic sensor to measure linear displacement. This was done at 0.5 volt increments as our motor is very powerful and would spin incredibly fast. And so we needed to have a lower increment of voltage to help us capture precise changes in displacement. One important aspect to note is that there's still a bit of spring clearance on the tachometer. What this means is that as the tachometer initially starts spinning, there will be no compression because there's still a little bit of linear distance before the spring meets the top of the tachometer before it can start resisting or compressing. Our table here presents our collected data. As the voltage increases, we can observe how the displacement in millimeters and the RPM values change. At 0 volts, the displacement is 62 millimeters and the RPM is 0. This is our offset. And as we increase the voltage in increments, we can see both corresponding increases in both displacement and RPM. For example, at 1.5 volts, the displacement increases to 69 millimeters, and it's more consistent over time. There's each increment of 0.5 volts shows an increase about 3 to 4 millimeters of displacement. Of course, with a linear relationship with RPM. By the time we reach 4 volts, we have a maximum displacement of 86 millimeters and at an RPM of 250. This data forms the foundation for analyzing the relationship between voltage, displacement, and RPM, and help us. So we have a slide that illustrates the calibration process and the relationship we establish between voltage, displacement, and RPM. The blue line on the graph represents the relationship between the voltage increase versus the RPM increase, while the red line represents the relationship between voltage and the, the linear displacement. These relationships were developed based on our collected data. Using the least squares regression, we confirmed the linearity of both relationships. For displacement, which is the blue line, the equation of the slope is 6.05x plus 60.9, when R squared value of 0.99, indicating a very strong linear correlation. For RPM, the equation is 62.5x when R squared value of 1, showing a perfect linear fit. And then on the next slide, the, the slope was implemented into the Arduino, which, as you can see here, with just the linear displacement versus voltage relationship, was implemented to the Arduino to calculate um, how the displacement will affect the reading on the electric LCD screen.
All right, as shown on the table, our overall percent errors were relatively low, and the highest percent error was 3.2% at 125 RPM, while the lowest percent error was 1.2% at 250 RPM. Since our spring constant was 1.66 newtons per millimeters, our maximum theoretical RPM was 400 RPM. During operation, our shaft experienced some wobbling due to the pressment bearings being too loose. Also, measuring the RPM mechanically through the stick and ruler wasn't very accurate due to the vibration and viscous effects from the bearing. All right, next slide. All right, in conclusion, the 5-volt tachometer proved to be a way to measure RPM mechanically without relying on electronic instruments. In our design, we used an ultrasonic sensor to measure the lift of the 5-volt tachometer, and that proved to accurately measure the motor's angular speed. However, during operation, the tolerances from the 3D printed components caused some wobbling. So to fix that, we use extreme press fits. And due to the wobbling, the sensor readings also fluctuated, so we averaged the readings and improved the calibration procedure to yield more precise findings. All right, next slide is our bill of materials. And there are about 18 items in total. And overall, our total cost was estimated at $125, which exceeded our budget. However, we already had most of the parts on hand, so the actual money we spent out of pocket was under $20. All right, that concludes our presentation. Thank you.